Hi, my name is Rebecca Post, and today I'll be talking about factor groups. I'm going to be talking about factor groups because as you move forward with abstract algebra, you might be coming into Galois theory. And in Galois theory, there are these things called Galois fields, which at their basis is a factor group. So in order to understand what a factor group is, you need to understand what those elements look like.
And elements of these groups look like cosets. So if you're given a group G and a subset H, then if you take any element of your group G and operate it with every element of your subset H, we would get a coset. If you operate on the left side, we get the left coset. If you operate on the right side, we get the right coset. Typically, in mathematics, we use the left coset, though this is just for consistency and not because of some inherent difference between the left and the right cosets, though they are not always equal. So to better understand this, we should walk through an example. If we have the group, the integer is mod 12 under addition, and we have the subgroup 0, 3, 6, 9, then we would create our cosets by taking any element of our group and adding it to every element of our subgroup. So we can start with 0, and we would get the coset 0, 3, 6, 9. Then if we added 1 to every element of our subgroup, we would get 1, 4, 7, 10. And if we added 2, we would get 2, 5, 8, and 11. Now I want you to notice here that we have every element of our group Z mod 12 represented in these three cosets. But we have not gone through every element of our group and added it to our subgroup. So let's keep going. We have 3 plus H, 4 plus H, 5 plus H, and then you could add the rest of them as well. Now, what you should also notice is that many of these cosets actually are the same set. So 0 plus H, 3 plus H, 6 plus H, and 9 plus H are all the same set. The same goes for 1, 4, 7, and 10 plus H, and 2, 5, 8, and 11 plus H. So you can see that our cosets are either identical or disjoint. So that means if you know that you have the coset that contains 1, you do not have the coset containing 2, because 1 is not contained in the same coset as 2 and can never be contained in the same coset. Now, an interesting result that comes from cosets is Lagrange's theorem, which says the order of the subgroup divides the order of the group, and that the order of G divided by the order of H is the number of distinct left cosets of H in G. So in our example that we've been using so far, we have G, which has order 12, and H, which has order 4, which means that we'd have 3 distinct left cosets, which we saw. We had 0 plus H, 1 plus H, and 2 plus H. Now the next thing we need to understand in order to develop factor groups are normal subgroups. Now we say that a subgroup H of a group G is normal if you can take an element of the group, operate it with H, and that is equal to H operated with A. In other words, the left cosets are equal to the right cosets for every element of our group. And we denote this as so. Now it's important to note that this doesn't mean that an element of G is commutative, but that there exists some H prime in our subgroup such that A operated with H equals H prime operated with A. One way that we often prove that a subgroup is normal is through the following theorem. A subgroup H is normal if and only if A operated with H operated with the inverse of A is contained in H for all A in G. So we should ask ourselves if the subgroup we've been working with, 0369 is a normal subgroup of our group Z mod 12 under addition. And in fact, we can easily see that it is because our subgroup is abelian, meaning that every element is commutative. Because every subgroup of an abelian group is normal. Now we are finally ready to look at factor groups. So if we have H, which is a normal subgroup of G, then our factor group, denoted G/H, is a set of distinct cosets A operated with H. And our factor group is a group under the same operation of G. So if, in fact, we can create factor groups, what would the factor group for the integers mod 12 under addition in our subgroup 0369 look like? Well, it would look like the set 0369, the set 1, 4, 7, 10, and the set 2, 5, 8, and 11, which we know you can also write as 0 plus H, 1 plus H, and 2 plus H. Now you might be wondering, as you think back to the earlier slides, why we chose to denote these as 0 plus H, 1 plus H, and 2 plus H, when we know that, for example, 1 plus H could also be written as 4 plus H. I chose to write these as 0, 1, and 2 because they were the smallest numbers, but you could have really written this anyway. Now we will see the choices you make here are important and is part of the reason that normality is important in a factor group, but we'll come back to that a little later. So what we need to do is check that 0 plus H, 1 plus H, and 2 plus H is actually in factor group. And the 4 qualities we need for a group are closed, associative, containing an identity, and containing inverses for every element of the group. So I don't have time to go through every element, but we're going to go through a few quick examples to try to convince you that this is in fact a group. So we can see that this is in fact closed. If we take 0 plus H plus 1 plus H, we're going to get 1 plus H. So if we take our two cosets, 0, 3, 6, 9, plus 1, 4, 7, 10. If you add 0 plus 1, you're going to get 1. If you add 3 plus 4, you're going to get 7. If you add 9 plus 10, you're going to get 19, which mod 12 is 7. So we're going to see that, in fact, it is closed. And another example, 2 plus H plus 2 plus H is going to equal 4 plus H, which we did not have represented in our statement of the group. But we know that 4 plus H is another way of writing 1 plus H. So we can see that it's going to be closed. The next thing we need to check is that our group is associative. So that means we want 2 plus H plus 6 plus H plus 4 plus H to be the same thing as 2 plus H, quantity of 6 plus H plus 4 plus H to be equal. So we can see that 2 plus H plus 6 plus H is going to give us 8 plus H. And then 8 plus H plus 4 plus H is going to give us 12 plus H. And we know that 12 plus H could also be written as 2 plus H and 10 plus H, which 10 plus H can also be written as 6 plus H plus 4 plus H. So in fact, we're going to see that this is associative. And our identity element is going to be 0 plus H, which, as you can see from the first bullet point under closed, because adding 0 plus H to any element is going to return that element. The last thing we need to check are inverses. So we're going to notice that in fact the inverses of our elements in the factor group are the same as the elements in Z mod 12. So in Z mod 12, the inverse of 2 is 10. But we are only using 0 plus h, 1 plus h, and 2 plus h to represent our elements. So, in fact, the inverse of 2 plus h is going to be 1 plus h, because it is in the same coset containing 10. And we can see that 2 plus h plus 1 plus h equals 3 plus h, which is another way of representing our identity element. So in fact, we do have inverses. Now, one thing I've kind of glossed over is the idea of well-defined. In addition to close associative, having an identity, and having inverses, our group also needs to be well-defined, which is why we need normality. Now, as we saw earlier, our subgroup is normal, so that's not going to be a problem. But to try to show you why normality is necessary in factor groups, let's look at a different example. So, if we have the group D3, which is the set of transformations on a triangle, then let's look at a non-normal subgroup, particularly the identity element and the flip through the left vertex of the triangle. If you don't believe that this subgroup is not normal, then take a minute and pause the video and try to prove this using the definition provided on the earlier slides. Now, using this subgroup and our group, our factor group is going to take this form. But as we saw earlier, each element of our factor group can be represented in multiple ways. So we also know that each element could be represented in this way as well. So to easily see where the idea of well-defined comes up, let's construct a Cayley table. So if we create a Cayley table using the second representation of our factor group, we would get these results. Now, if we just change our representation of, for example, the rotation of 120 degrees composed with our subgroup, which is what well-defined means. Well-defined means that if we change the representation of our element, we're going to still get the same result. So if we change the representation to the flip through the right vertex of our triangle, composed with the subgroup, our second row changes. And in fact, we can see that the middle entry of our table changes to the identity element times our subgroup, which is not the same coset as the rotation of 240 degrees composed with our subgroup, because, as we noted earlier, all cosets are either distinct or identical, and we know that the subgroup contains the flip through the left vertex if it contains the identity element, which means that in fact we don't have well-defined, so this cannot be a group. So now that I've showed you how to create factor groups and I've tried to explain the importance of normality, you're ready to move on and look at quotient rings. Quotient rings are very similar to factor groups or quotient groups, except we're going to have a similar problem to worry about with the well-definedness of the operation, since we have now a second operation in rings. I hope you enjoyed this talk, and I wish you the best of luck with your further endeavors into abstract algebra. Thank you.